Hello, I'm Michael O'Connell, and in this video, we are going to use the cubic polynomial expression for the compressibility factor that we derived in a previous video. And what we're going to do is find the roots of that equation using Cardano's formula. And as I said in that video, what that is going to allow us to do is find specific volume values from the compressibility factors we get, which would be the roots of that cubic polynomial. So Cardano's formula has this cubic polynomial expression in which it uses the coefficients a, b, and c. Now notice on the board that would be different than what I had because I had a, b, c, and d for a generic cubic polynomial. But this will work for us because we just had z cubed as our first term. And we just have to remember that whatever I had for b, c, and d is what we're going to be using to compute these roots. So I wanted to show this on the screen as well. What I did to keep things more organized is I created a document in which I typed out all the steps that we did when we derived that cubic polynomial expression for the compressibility factor. And then at the end here, I put this right there with a, b, and c in the right places. And then from what we had before, I put in what these coefficients in front of z squared, z, and then the constant would be respectively, such that we can use this in our code. Because what we're going to do now is actually create a function or two in Python to determine these specific volume values. And remember that when we're below the critical point, we're going to have some specific volume for material in the liquid phase and some specific volume value for material in the vapor phase. And then there is going to be a case when we're above the critical point, so some pressure and temperature combination that is above that point, in which there would just be one specific volume value. And as you can imagine, that is going to be the case with Cardano's formula, in which there's one real root. And of course, I believe, yes, there are imaginary roots, but that's not going to be our focus, obviously, because we just want that actual specific volume value of that material that's past the critical point. And we're going to use the same substance we used in the previous video when we made isothermic curves of pressure versus the specific volume for water. So that is what I'm going to code this in, literally the same place in Collaboratory. And let's get started. Let's write a function to compute the roots based on the coefficients a, b, and c. So we'll define a function called cubic roots, and the inputs will be our coefficients. That will be the a, b, and c values there. And then it tells us in Cardano's formula to first compute q and r. So that's exactly what I'm going to do here. As I stated before, there's going to be two situations with Cardano's formula. One case is going to have 3 real roots, and then the other is going to have 1 real root. And as we can see here in this document, the next case we have is if r squared is less than q cubed, then we have to compute this theta value that we're going to use to compute 3 real roots. So let's do that as our first case. So we'll make this condition here, and it's going to be if r squared is less than q cubed, what are we going to have? Well, we're going to have theta equals arc cosine r over, and q cubed square root is q 3 over 2, so we could do q to the 1.5 power, and I forgot we need to use numerical Python for that, so np. Now b, that should be way up here. Yep, import np as np, and just making sure I have it. Okay. And what are we going to do next? Well, what we're going to do next is use that theta value in finding these roots. let's express our roots in our code here. So we'll call it roots equals. Notice that we have -2 times radical q, and we have minus a over 3 in all of these expressions. The only difference is the expression inside our cosine. So what we can do, and we know we're going to have 3 roots, is we can just make an array in which we find the cosine of each expression in the array. So we can just make these expressions different elements of that 1/3 array. So that's what I'm going to do here, just to make things a lot easier on ourselves. Now let's write our return here. What we would want to return is our roots that we computed, but what we are going to want to do here is actually sort them in a specific order. We know that we're going to get 3 real roots, and what we would use those roots to do is find our specific volume values. But we know that the intermediate value, so the one that's not the lowest and the one that's not the highest, is artificial, as I've said multiple times. And the lowest one is going to be the material in the liquid phase. In this case, for what I have in Collaboratory, we are using water, I believe, from a previous video. Yep, that's right there. And then the higher value is going to be the one in the specific volume in the vapor phase. So NumPy has something really cool that can do that, and it's np sort roots. Okay, and that's just going to sort our array, and because we use this array, it's going to be an array of those 3 real roots. So this will sort those in order for us. Okay, now we have something else that we have to consider, which is that there's another situation, isn't there? So we'll just, since there's only one other situation, I'll just use else. And what it's telling us to do, it says otherwise compute this. So let's write a formula for a. And then it says where the sign of the square root is chosen to make that greater than or equal to 0. Okay. So if q and r are both real, equations are equivalent to, okay, so yeah, they want us to factor in the sign. So this is going to be based on the sign of r up here. That's going to dictate the sign of a, and actually it's going to be the opposite because we see the negative. The SGN, what that stands for, if r is 85, then sign of r is +1 because the sign is positive. But if r was -8, this would return a -1. But again, we have to notice that there is that negative sign, which just means that a is going to be the opposite of that. So let's write a formula for a. And if you're wondering, like, oh my goodness, like, what are these letters? I don't understand. Don't worry, because we literally just did something very similar for the case with 3 real roots, because we're just following the directions of a Cardano's formula. It told us to compute this theta, and I willingly obeyed so that we could find our 3 real roots. And what we're doing here is the same thing, except in this case, we're actually going to be finding the 1 real root. So let's see where this takes us, and let me write the code for a. Now let's do the next thing that Cardano's formula demands, which is computing b. And this is actually also going to depend on a. And let's just write a quick conditional. So we'll just do the version where we do it in one line. So b is going to be 0, as they say, if a is equal to 0. And notice here that I'm going to use 2 equal signs because this isn't an assignment. This is a condition in which a is equivalent to 0, and you have to use 2 equal signs in that case because we're not assigning a value to a variable. And then else, so just anytime a is not equal to 0, it's going to be q over a. And what are we going to return here? Well, we are going to return one root, and this is defined as, let's see, x1, so this is a plus b minus a over 3. And it looks like we're good. Now we're ready to use our cubic roots function to actually find specific volume values. So let's define a new function to find specific volume values. We'll call it cubic volume. And the specific volume is going to depend on pressure and temperature, so that is what our function will take in. And then what do we need first? Well, we're dealing with a generic cubic equation of state. And fortunately, we are operating under the same notebook that I used to make our isothermic curves of pressure versus specific volume in a previous video. And what we had to do for that is we had to find the coefficients of the general cubic equation of state, A, B, epsilon, and sigma. And we're going to need those again to find the specific volume values. So I'm going to actually put that in our function here, and we're just going to unpack that into our coefficients. A, B, epsilon, sigma. Awesome. Then, if you recall, when we derived the cubic polynomial for the compressibility factor, we made some substitutions. Specifically, we used beta and Q. And here, I have in a document the steps that we took that I had afterwards to kind of organize what we did in the video in which we derived the cubic polynomial for the compressibility factor. And the reason I did this is because it's typed up, it looks nice, and it's very easy for me to use when we're writing this code, because I wanted to make another video to show how we can actually apply what we did on the whiteboard to maybe a real-world application in which we need to find the specific volumes. So that is the reason for why I did this, but for all intents and purposes here, we are going to need beta and Q. But before we do that, I think it would be easier for me to return what we want, because this will allow me to kind of work backwards and explain why I'm going to put everything that we need into our function. So what we want to return is we want to use the cubic roots function that we've made, because we're going to know these coefficients because we're going to have expressions for them here. Okay, and these are not made up or new. This is exactly what I had on the whiteboard. I just actually organized it. And remember, there was nothing in front of the z cubed. And then all I did was consolidate all the non-z terms in front of each, whether it was the z squared or z or just constant values here. So that is why we're going to need beta and Q. But specifically, what we're going to end up finding is we're going to find z. And from there, that was the whole point of deriving the cubic polynomial expression for the compressibility factor, because what we're going to end up returning is v. And v, if you recall, is going to be z times r times t divided by p. So that is going to be our return. So hopefully that gives you kind of some more context as to what we must include here. So what z is going to be equal to, again, that was our cubic polynomial, right? So we're going to use the cubic roots. The only difference is now we actually are going to supply what a, p, and c are. And that is what I have these expressions here for. So I'm going to type those in a second. But as you can see in these expressions, we have beta and we have Q. Well, what the heck is that? Well, if we remember, beta and Q had A's and B's in them too. And that's why we need to assign those and define them in our function. So beta is equal to the product of B and the pressure divided by R times T. And then Q is equal to A divided by, it's easy to get lost in all the text, b times r times t. Okay, perfect. So now what I'm going to do here, scroll down so that you can see this, is I'm going to put this in for A, this in for B, and this in for C. Alright, now let's try to see if this thing will work. So, to keep everything in order here, I'm going to do runtime all when I do this. And then, yeah, so we'll just try like 10 million pascals because we can look at our graph here, right? So just something reasonable, 10 million. 600 kelvins maybe. Let's see what that gives us. And one value, okay, so that's obviously not correct. So something must be wrong in this equation here, which leads me back to this. And let's just check that everything's correct. So we have Q A squared together, 3 times B minus, subtracted from each other, divided by 9. That's all good. 2A cubed, got that. 9AB, 27C minus and plus, divided by 54. That's all good. Our conditional is correct. We're going to find it somewhere. So we know this shouldn't return just one value because we're above that critical point for water. And actually, well, here, let me, just to make sure, let's look at the critical pressure. Okay, that is 1, 2, 3, okay, 22. So we're below that. Okay, we're below the critical pressure, which means I don't even have to look to see if we're below the critical temperature or not because it doesn't matter. We're below the critical point. That's what matters. Which means that we should be getting 3 specific volume values. So something is wrong with our code. So after that minor digression, let me look back here at theta. Okay, we have arc cosine. We used numpy to do that. That's all well and good. Let's look at our roots. Minus a over 3. That's on the end there. These are all correct. Okay, maybe it's the A and B, potentially? And if we look... Uh-oh. Oh, yep. Okay, we do have a problem. It's very, very subtle, but you see here in the equation for A that we used, we're subtracting R squared and Q cubed, and right there we have a plus. One small error like that and nothing works. So let's try this again. And nothing changed. So something is clearly wrong here. So after looking through the code above from the last video, I found that everything is working fine and it's still all correct. So clearly there is a problem that we have with the specific volume that is being spit out because, like I showed before, we should be getting 3 values. So that gave me, obviously, a good hint here. And we know, for us, that we have R and Q, and that Q cubed must be greater than R squared to return 3 specific volume values. And that clued me into where the mistake might be, and I did actually find it. What we did, and really by we I mean me, is we had 2A quantity cubed instead of 2 times A cubed. And if you can do kind of a quick math on that, you're actually cubing 2 as well, right? So what happened is this R value was artificially high, so much so that it was actually greater than Q cubed. Thus, our final return had only one specific volume value, when really it should have 3 roots that are sorted in order. And then those roots are used in here to spit out our specific volume values. So let's adjust that and see to it that that actually is what happened. And it does appear that I have everything correctly. We'll put an asterisk there to multiply the 2. And we'll do runtime all to make sure everything's correct. And hopefully we get 3 values this time. And there you have it. We get 3 values. So like I said, this intermediate volume here in cubic meters per mole, we don't need to worry about that. And even though it is real, it is artificial in the sense that it doesn't represent any actual physical volume that would be present in real life, because we are only going to have this specific volume for our liquid water and this specific volume for the water that's in the vapor phase, because we are below the critical point. So hopefully those 2 mistakes are good lessons for me and good lessons for you, the viewer, as to check your code more often as you're running it. And hopefully me explaining how I caught my mistake is also helpful in showing how you can actually deduce where a small error might be that might cause your code to be returning faulty values. But as you can see, it's very, very important to understand what we're doing here when we're trying to use the cubic equation of state, because had I not known that, I might have just not tested anything and not looked at what the critical pressure and temperature might be. And I might have just thought, oh, 600 kelvins and 10 million pascals is above the critical temperature and pressure, respectively, for water. And that's obviously not the case. So the reason I was able to find that error is because I actually checked what those were. So I was able to know that, hey, I need to be getting 3 specific volume values. Hopefully after watching this video, you understand a lot more about Cardano's formula and how useful it can be, especially when we're dealing with the cubic equation of state, and how we can actually use it when we know the pressure and temperature to find specific volume values for a substance based on whether it is below the critical point or above its critical point even. And I hope you also learned a lot more about how to effectively find your mistakes when you're writing code based on the concepts that you know. So thank you so much for watching.